The next area of study is acute responses to exercise. So these are the immediate responses to the various body systems during exercise and immediately thereafter. This one's looking purely at cardiovascular. Remember, cardio means heart, vascular means the vessels and the blood that travels through them. So not a lot of detail in the key knowledge and skills here, but basically identifying a range of acute responses to this body system, the cardiovascular, and explaining the mechanism. So how does this go up or how does this go down? The question is not that different to the key knowledge. What happens to our cardiovascular system when we exercise?
Guiding questions are again provided to help you structure some responses and notes from the particular PowerPoint, always supported by the text and now the web links that make sense. So you're encouraged to write these down, annotate as you would per an exam, and then to flesh out the details here and where you come up with blanks or problems or confusions. That's when you start the conversation with fellow students and myself.
Working heart rate graph, a period of rest preceded by a work bout and then a recovery. Now the heart rate goes up in response to exercise, we know that, but what makes it increase and why does it in fact increase a moment before exercise start? That's called an anticipatory heart rate rise. How can we explain that? This graph here shows both heart rate and oxygen uptake. Oxygen uptake is VO2. We're just looking here at the relationship of heart rate to exercise. So it increases in a linear fashion, so that's a straight line fashion, and it will increase as intensity increases up until maximum heart rate. And just recall that maximum heart rate is 220 minus your age. So this linear relationship up until max is slightly different to the relationship with stroke volume, which we'll look at shortly. Here's a diagram to explain the relationship of stroke volume during exercise. And unlike heart rate, which is linear up until max, stroke volume is linear up until submaximal work. And in this particular case, it looks like approximately 55 or 60% of VO2 max, we get the stroke volume plateauing. So if this was the heart rate line, that would be a straight line, almost at 45 degrees if you like. But stroke volume plateaus at submaximal, so it's quite unique. Try and remember that. And that's because the heart only has so much stretch. It can't keep filling up as the cardiac output increases, or else your heart will blow up like a water bomb, I suppose. So it's finite in how far it can stretch. Here's the same relationship just from a different textbook, just to show you the same data, but just in a slightly different representation. Realistically, again, it looks like at about 60% of VO2 max, stroke volume plateaus, and that's because it cannot continue to increase its capacity and take more blood being returned to the heart. It does have a finite capacity, but it will increase in response to exercise up to submaximal. Thereafter, it will plateau. This graph here simply shows cardiac output, and cardiac output is a combination of heart rate and stroke volume. So the beats per minute of your heart times the milliliters per beat from the stroke volume gives us the cardiac output, so the volume of blood that circulates through the body per minute. And this increases in a linear fashion up until max. It looks like a resting figure here is approximately 5 litres per minute, up to about almost 25 litres per minute at 100% VO2 max. Blood pressure is slightly more complex than stroke volume and heart rate insofar as there is 2 readings for blood pressure, as you'll be aware. Systolic is when the heart contracts, so that's the force of the blood on the arteries when the heart contracts, and it should make sense that that goes up as exercise intensity increases. Diastolic, which is the lower reading, is the pressure on the arteries when the heart is in diastole or relaxes. So hopefully that too makes some sense that it doesn't change significantly. It's either held pretty constant or in fact there can be a slight decrease because of another variable we'll talk about later called decreased peripheral resistance. But in essence it just means as there is less pressure on the blood returning to the heart, the relaxation phase of the heart, or diastole, can remain constant or in fact even decrease. Remember, a normal BP is about 120/80. This graph here serves to show what happens to both blood pressures. As I said, systolic is easier to understand in my mind. If systole means contract, it makes sense that that increases in a linear fashion up until max. Diastolic is when the heart is relaxing and filling with blood, and that is relatively constant or can in fact can in fact decrease because of this reduced peripheral resistance in the extremities of the body through vasodilation of the vessels. It's actually easier for the blood to return to the heart, so the diastolic blood pressure can in fact drop. Little fancy creature here is called a sphygmomanometer. I don't think you'd ever have to spell it. I just call it a blood pressure cuff. But you can see on the dial there, systolic on top, diastolic on the bottom. That's 118/78, and the traditional, typical resting adult figure would be 120/80, so that's about perfect. The pulse at 70 is also bang on 70, or 72 is our average kind of heart rate. The unique feature here is it's measured in millimeters of mercury. So mmHg is the measurement unit for the blood pressure cuff. And I've certainly seen questions in exams with that unit of measurement put on a graph, and I guess the trick was for people to work out what in fact was being measured. This graph just shows us for a series of exercises what happens to blood pressure. It's obviously trying to capture realistically the systolic level, because at rest it looks like the person sitting down and watching telly's a fraction over 100 mmHg, and then it increases in line with, I guess, the nature of the exercise. And in particular, if you looked at the trend here, weight bearing or weight resistance exercise puts greater strain on the heart and blood pressure than does a non-weight bearing or cycling. And in fact, lower body with a double leg press compared to the two-arm curl puts greater pressure on. And I can understand that insofar as using the legs with the blood going to the muscles there requires greater force for the heart to get the blood to those working muscles, rather than the upper body, which is closer to the heart. The redistribution of blood flow to working muscles should make perfect sense with what you recall from energy systems, insofar as when the body starts to work, it requires oxygen to break down fuels, so we prefer to have oxygen to break down fuels, so it starts increasing blood flow to the working muscles, which carries with it more oxygen and also helps remove the waste. Now, this particular graph shows that at rest, there's about 15% of our blood going to the skeletal muscles because we're not working, the muscles don't require it, and the 85% remainder goes to our internal organs, brain, heart, kidneys, etc. When we start to work, that can get flipped around on its head if we're working maximally. Here's another pie chart to show the same data, roughly the same numbers. I think it's actually easy to remember 20% to 80%, but you can remember whatever you like. Certainly if you're given a question in an exam, you'd have to deal with the exact numbers in front of you. But roughly 20% of our blood flow while at rest goes to our skeletal muscles because they're not working hard, they don't require that oxygen, and 80% goes to our internal organs. And this graph comes from the third textbook, and it's just a different way of, again, showing the same information. The advantage of this one is it does cater for different levels of exercise intensity on the right-hand side. So be mindful, you wouldn't talk about an 80-20% shift or reallocation of blood flow if the person wasn't working maximally, but that's what the body can do. The mechanism responsible for that increased redistribution of blood flow to working muscles is vasodilation to those same muscles. So any working skeletal muscles, as we begin exercise, will begin vasodilation of vessels to that particular site. At the same time, the vessels carrying blood to the brain, kidney, liver, all the internal organs can start to reduce blood flow via vasoconstriction. So those two terms are pretty important. Vasoconstriction, like a boa constrictor, the snake that chokes its prey, shuts down blood supply. It doesn't shut it off completely, but it narrows the vessels so there's less blood going through. And the vasodilation, if you like, opens the floodgates to increase blood flow, which carries all that beautiful oxygen to the working muscles. The other aspect of redistribution of blood flow can be seen when we vasodilate our vessels to the skin to give a cooling effect, to cater for thermoregulatory fatigue. So here's some of our blood, which we'd rather be going to the working muscles, to be honest, to provide oxygen for the working muscles, but some of it has to be rediverted away from the core as our body temperature increases to the surface of our skin, hence this lady's red face, to give up heat via radiation, convection, conduction, all those crazy science terms you might remember from Year 9 or 10 science, to cool the body down. So some blood is redistributed to the skin surface to help cool the body down. Increased venous return, if you just look at the terms in front of you, talks about an increase in the return of blood via the veins to the heart. And it makes perfect sense. If everything else more or less goes up with heart rate and stroke volume and cardiac output, etc., there's more blood coming back to the heart. and that increased blood to the heart helps explain the increased stroke volume, and so we go chasing our tail, that whole chicken and the egg scenario. Now, part of the reason there is more blood returning to the heart is that it's easier for the blood to get back because there's decreased peripheral resistance, which just means because of the vasodilation in the skeletal muscles, it's easier for that blood to return to the heart. At the same time, that decreased peripheral resistance also helps to explain a leveling off of diastolic blood pressure, or in some cases, a drop in diastolic blood pressure. This little image here talks about total blood volume and separates it into formed elements and plasma. Plasma is what I'm talking about now because 90% of plasma is water, and that's what we're going to lose via sweating. So 55%, so over half of your total blood is plasma, and then 90% of that 55% is actually water, and that's what we lose when we start to sweat. The other 45% called formed elements are your red blood cells, white blood cells, and platelets. So obviously there's hemoglobin within the red blood cells, which is almost all of your formed elements, and together they form total blood volume. So if we lose the fluid from the plasma component, we drop blood plasma. Blood plasma is part of total blood volume, so we also drop total blood volume level as well. So this diagram serves to show us what it actually looks like once we start to lose some fluid from the blood plasma because we've been sweating. So on the right hand side you can see there's a slightly lower level of blood plasma volume. The formed components, so the red blood cells, white blood cells, platelets, still hold at 45%. So if you like, the relative concentration of the blood on the right hand side is thicker with the cell component because it's lost some of the water. It's a bit like a stronger cordial, if you like. We've dropped some fluid out to help us cool down via sweating, but the same red blood cell, white blood cell, platelet component remains. Now, it does make the blood thicker. It does make it harder for the aerobic energy system to work, if you can remember anything about your energy systems. It's got a whole lot of fatigue-related ideas that we'll explore in coming weeks. But essentially, blood plasma volume decreases, as does total blood volume. Just to clarify, the cooling down aspects of the body, which start to go into the fatigue part of the course, but there's two aspects that lead to possible fatigue as cardiovascular responses to exercise. So the first is the sweat, where we lose fluid from the blood plasma via our sweat glands, as you can see with Rafa there dropping sweat off his nose and chin. That's different to the cooling mechanism that the body does by just redirecting blood to the skin. Okay, so there's two mechanisms there. We send some blood to the surface of the skin, and then we also give up fluid from blood, which cools us down via evaporation. So sweating via evaporation is far more effective, but both serve to help cool the body and bring our core temperature down. And so here's just an image of what's actually happening with the sweat glands. So the capillaries, still relatively close to the surface of the body, give up some of the fluid from the plasma through a sweat gland. When that forms water that water forms on your skin surface, hopefully with the breeze or a cooler atmosphere outside, we start to evaporate that and cool the body down. Finally, here's my mind map trying to find a way to arrange all the information from the cardiovascular system. As I've said a number of times, there is very much a chicken and egg and chasing your tail relationship to all these things because they do interrelate, and it's pretty difficult to work out the very first thing. But I've tried to do that. If you look at it like a clock face, and the top right-hand side is 1 o'clock with the endocrine system, I've kind of started there with the heart, and I've worked all the way back around to Venus return. But you could certainly rearrange this in another order that made sense for you. But the red text is the parameter, and then the blue box is the mechanism that explains how that goes up or down or stays constant. Have a go at making your own.